Welcome to this journey through the coldest frontiers of existence, where we will venture from the frozen landscapes of Earth to the farthest reaches of interstellar space, unraveling the mystery of a place so frigid that it defies common sense and challenges our understanding of how the universe works. Most people imagine that the coldest place in the universe must be the void between galaxies, the infinite nothingness that stretches between the great islands of matter in the cosmos. But as we will see, the truth is far stranger and far more fascinating. Before we even step beyond our own planet, we must confront what we mean when we say cold, because temperature is not just a casual sensation, but a measure of energy, the speed at which atoms and molecules vibrate, collide, and exchange heat in an endless microscopic dance. When something is cold, what we really mean is that its particles are moving more slowly, transferring less energy to one another. And when we speak of the ultimate cold, we are speaking of absolute zero, the point at which atomic motion would theoretically cease altogether. This concept of absolute zero was first explored in the 19th century by Lord Kelvin, who created the Kelvin temperature scale, defining 0 Kelvin as the complete absence of thermal energy, an unreachable but immensely useful reference point for scientists. In laboratories today, physicists can cool gases to billionths of a degree above absolute zero using techniques like laser cooling and evaporative cooling, creating exotic states of matter such as Bose-Einstein condensates, first predicted by Satyendranath Bose and Albert Einstein in the 1920s. These condensates behave in strange and beautiful ways, with particles acting as a single quantum wave, moving in perfect harmony as though they are one entity, revealing a world where quantum mechanics rules over classical intuition. Such experiments remind us that cold is not simply the absence of heat, but a gateway to deeper truths about reality, peeling back the layers of the universe to show us what matter does when stripped of almost all its energy. Armed with this understanding, we turn our gaze to the sky because nature has its own cryogenic laboratories scattered across the galaxy, places where dying stars, collapsing clouds, and expanding gases reach temperatures lower than anything we can achieve on Earth. One such place is the Boomerang Nebula, a cloud of gas located about 5,000 light-years away in the constellation Aquarius, famous for being the coldest naturally occurring object ever observed, chilling itself to just 1 degree above absolute zero. This frigid wonder was first discovered in 1995 using the Swedish ESO submillimeter telescope in Chile, and its discovery stunned astronomers because they expected a cold nebula, but not something colder than the cosmic microwave background itself. The cosmic microwave background, or CMB, is the faint afterglow of the Big Bang discovered by Arno Penzias and Robert Wilson in 1965, filling the universe with radiation at a temperature of about 2.7 Kelvin, which acts as a baseline below which temperatures should not normally fall. Yet here was the Boomerang Nebula, colder than the very background of space itself, forcing scientists to re-evaluate their models of stellar outflows and the efficiency of adiabatic cooling during mass ejection from dying stars. The process works like this. As the dying star expels gas at speeds over 150 kilometers per second, the gas rapidly expands, and as it expands, its energy spreads out, causing its temperature to plummet, much like how compressed air from a can feels cold when released, but on a far grander scale. When astronomers turned the Atacama Large Millimeter Submillimeter Array, known as ALMA, toward this nebula, they saw its hourglass shape in breathtaking detail, revealing streams of gas forming a ghostly structure larger than our entire solar system. The image was so precise that scientists could watch how the gas was sculpted by stellar winds, hollowing out cavities and chilling itself to a temperature lower than anywhere else in the known cosmos. This made the Boomerang Nebula a natural laboratory for studying the physics of extreme cooling, giving astronomers insights into how stars lose their mass in their final stages and how such processes enrich the interstellar medium with heavier elements. But our quest does not end with this single nebula. There are other places in the universe where cold reigns supreme, each with its own story to tell, each challenging our idea of where the ultimate cosmic freezer might be found. Consider the dark molecular clouds afloat between stars, enormous accumulations of gas and dust where temperatures hover around 10 Kelvin, cold enough to slow chemical reactions to a crawl and allow fragile molecules to form without being torn apart by radiation. It is in such clouds that future stars and planets are born, meaning that the same cold that seems so hostile is in fact the cradle of creation, a paradox that reminds us of the dual nature of the universe where death and birth are intertwined. The famous Orion Molecular Cloud Complex, for instance, is a stellar nursery where astronomers can watch protostars ignite, slowly warming the frigid gas around them, turning dark patches into brilliant beacons of light as nuclear fusion begins. These clouds are so cold that radio telescopes must be used to study them because they emit almost no visible light, whispering their secrets in the millimeter wavelengths that pass through interstellar dust. This is why observatories like ALMA and the James Clerk Maxwell Telescope are built at high altitudes in dry deserts, where the air is thin and water vapor cannot absorb the faint signals arriving from across the galaxy. By carefully mapping these frigid regions, scientists can trace how gas collapses under its own gravity, how filaments of material form, and how the seeds of stars and planetary systems take shape in the coldest corners of space. The extreme cold of these molecular clouds is not just an astronomical curiosity, but a fundamental requirement for the chemistry of life, because only at such low temperatures can delicate molecules like formaldehyde, methanol, and even amino acid precursors form and survive long enough to seed future planets. Astronomers using the Herschel Space Observatory have detected water vapor, carbon monoxide, and complex organic molecules in these frigid regions, hinting that the first steps toward biology are taking place in the dark, cold heart of space. This discovery carries profound implications because it means that cold, far from being an enemy of life, might actually be one of its greatest allies, preserving fragile compounds until the moment they can be incorporated into new worlds. But even these molecular clouds, cold as they are, cannot compete with the Boomerang Nebula's astonishing temperature, which remains our benchmark for natural cosmic refrigeration and a subject of intense study for astrophysicists. To truly appreciate how remarkable this is, consider that the temperature of interstellar space is set by the cosmic microwave background at 2.7 Kelvin, meaning that the Boomerang Nebula is somehow managing to radiate away heat faster than it absorbs it, a feat that seems almost paradoxical. The key lies in its rapid expansion, which acts like a cosmic refrigerator, converting the internal energy of the gas into kinetic energy of motion, causing its temperature to plummet as the gas races outward into the emptiness. This is the same principle behind adiabatic cooling in our atmosphere, where rising air expands and cools to form clouds, except here it is occurring on a scale measured in trillions of kilometers, sculpting a nebula larger than the solar system. When astronomers peer into this nebula with ALMA, they see a structure shaped by stellar winds, revealing not just a frozen ghost but a dynamic process that is ongoing, a snapshot of stellar death caught in mid-breath. What makes this even more fascinating is that we are observing this event in real time from 5,000 light years away, meaning that what we see today actually happened thousands of years ago, a frozen message from the past traveling across the galaxy to reach us. This interplay between extreme cold and the life cycle of stars teaches us that the universe is not static but constantly transforming, with every dying star sowing the seeds for the next generation of stellar systems. In a sense, the Boomerang Nebula is not just a curiosity but a teacher, revealing how energy and matter behave under some of the most extreme conditions imaginable, offering lessons that may one day help us develop better cooling technologies here on Earth. Engineers studying cryogenics and superconductivity are deeply interested in how such extreme natural cooling works, because achieving lower temperatures is key to building quantum computers and other advanced systems that require near-perfect isolation from thermal noise. The connection between cosmic cold and human innovation might seem tenuous, but history has shown that astronomical discoveries often lead to breakthroughs in technology, from radio communications inspired by Maxwell's equations to GPS systems made possible by Einstein's theory of relativity. Thus, when we study the coldest places in the universe, we are not simply satisfying curiosity, but also expanding the boundaries of what is possible, exploring the ultimate limits of thermodynamics that govern everything from engines to ecosystems. Our journey through this first chapter continues as we look at other contenders for the title of coldest place, including the shadowed craters at the Moon's south pole, where NASA's Lunar Reconnaissance Orbiter has measured temperatures as low as 26 Kelvin, colder than Pluto's surface. These craters are in permanent shadow, never seeing sunlight for billions of years, allowing volatile ices like water, carbon dioxide, and ammonia to remain frozen in place since the early days of the solar system. The Artemis program aims to send astronauts to this region, partly because these ancient ice deposits could provide water for drinking, oxygen for breathing, and hydrogen for fuel, turning the Moon into a stepping stone for deeper space exploration. Compared to the Boomerang Nebula, the Moon's craters may seem warm, but they represent the coldest places ever measured on a planetary body, and they remind us that cold is not rare but widespread, a crucial player in shaping planetary environments. Even colder still are the dark regions of interstellar space where no stars shine nearby, where cosmic rays provide the only source of energy, and where temperatures hover just a fraction above the universal background. In these regions, atoms move so slowly that chemistry is nearly frozen, forming exotic molecules on the surfaces of dust grains, which then drift silently for millions of years until a shockwave from a supernova or a passing star stirs them into motion. Each of these environments tells part of a larger story, that cold is not just a condition but a process, an active sculptor of cosmic structures, a force that slows time in some sense, stretching out the lifespan of fragile systems that would otherwise vanish too quickly to be noticed. The study of these slow-motion cosmic environments has led to some of the most precise measurements in modern astronomy, allowing researchers to calculate the densities, pressures, and temperatures of interstellar clouds with astonishing accuracy. Radio astronomers often use molecular traces such as carbon monoxide lines to map these cold clouds, because CO glows faintly at millimeter wavelengths, revealing hidden structures in what would otherwise be completely invisible regions of space. The data gathered from such surveys helps build three-dimensional models of molecular clouds, letting scientists see how filaments form, twist, and collapse under gravity to form future stars, a process that can take millions of years to complete. In this sense, the cold is a collaborator in creation, slowing down atomic motion so that gas does not dissipate too quickly, allowing gravity to gather material together until a critical density is reached and nuclear fusion can begin. Without such cold phases, stars would ignite too quickly or not at all, and the balance between cooling and collapse is one of the most delicate dances in the universe, shaping the distribution of galaxies and the conditions for habitable worlds. Astrophysicists such as Subrahmanyan Chandrasekhar studied these balances in detail, describing how pressure and temperature compete with gravity, leading to insights about the maximum mass a star can have before collapsing into a black hole. This shows that even the coldest, quietest regions are connected to the most dramatic events in the cosmos, because without these frozen cradles, there would be no stars to explode, no supernova to scatter heavy elements, no planets for life to arise on. As we reflect on this, we are reminded that the search for the coldest place is not just about finding a number on a thermometer, but about understanding the cycles of matter and energy that shape the destiny of galaxies. Returning to the Boomerang Nebula, we see a dying star's last breath frozen into a cosmic hourglass, a brief but spectacular phase that will eventually give way to a planetary nebula, and finally, a white dwarf star. This transformation will take tens of thousands of years, but thanks to the speed of light, we are witnessing a moment that has already passed by millennia, a cosmic time capsule preserved in photons that have traveled across space to meet our telescopes. The more we study this nebula, the more we learn about how stars shed their outer layers, how fast winds sculpt these shells, and how energy is radiated away into the cosmic night, leaving behind structures that glow faintly in infrared and radio light. One could almost think of the Boomerang Nebula as an artist painting a frozen portrait of its own demise, a masterpiece written not in pigment but in hydrogen, carbon monoxide, and dust grains chilled nearly to absolute zero. And while the Boomerang Nebula currently holds the title of coldest place in the known universe, researchers continue to scan the sky with instruments like the James Webb Space Telescope, looking for other extreme objects that might be even colder or stranger. Future observations could reveal similar nebulae in other parts of the galaxy, each one a unique experiment in natural refrigeration, giving us a broader understanding of how mass loss and cooling affect stellar evolution. And this search is not limited to objects outside our solar system, because even here at home in laboratories on Earth and experiments on the International Space Station, physicists are pushing the boundaries of low-temperature physics ever closer to absolute zero. NASA's Cold Atom Lab, launched to the ISS in 2018, creates Bose-Einstein condensates in microgravity, allowing researchers to study quantum gases for longer times than possible on Earth, unlocking new insights into quantum mechanics and possibly future technologies. These space-based experiments are not just scientific curiosities, but may pave the way for advances in navigation, communications, and even tests of fundamental physics such as the equivalence principle of general relativity. The connection between the coldest laboratory in orbit and the coldest nebula in deep space is profound, showing us that whether natural or artificial, extreme cold is one of the most powerful tools for revealing the hidden laws of nature. In the quiet of these experiments, just as in the silence of the Boomerang Nebula, we find that cold strips away the noise, allowing the underlying patterns of the universe to emerge with breathtaking clarity. The phenomenon of extreme cold allows physicists to slow atoms to a crawl, making their quantum behavior visible in ways that were once purely theoretical, turning the laboratory into a window on the quantum world. At temperatures within billionths of a degree above absolute zero, atoms condense into a single macroscopic quantum state, behaving as though they are one superatom, an achievement first realized by Eric Cornell and Carl Wyman in 1995. This discovery of the Bose-Einstein condensate earned them a Nobel Prize in 2001, demonstrating that when motion is slowed enough, matter undergoes a kind of phase transition revealing properties of nature hidden at ordinary temperatures. In many ways, the search for cosmic cold parallels the search for laboratory cold, because in both cases we are stripping away energy to reveal the underlying order of matter and the forces that govern it. When we peer into a molecular cloud or a cryogenic chamber, we are looking at nature in its most stripped-down state, where random motion gives way to structure, where entropy is temporarily tamed enough to let us glimpse creation's blueprint. This is one reason astronomers are so fascinated by the Boomerang Nebula, because it offers a naturally occurring version of this stripped-down universe, a snapshot of gas so cold that its internal energy is almost gone, like a cosmic still life. Instruments such as the Atacama Large Millimeter Chong Submillimeter Array, ALMA, have been used to study this nebula, capturing exquisitely detailed maps of its hourglass-shaped outflow, showing how the gas streams expand and cool in near-perfect symmetry. These maps reveal not just temperature but motion, density, and chemical composition, letting scientists piece together the life story of this star, from its stable main sequence days to the moment it began to shed its outer layers. Such work is slow and meticulous, but it has transformed our understanding of how stars evolve, how they die, and how their deaths seed the next generation of stars with the raw material for planets and perhaps life. In a way, every cold nebula is both a graveyard and a nursery, marking the end of one stellar life and the beginning of many more. A reminder that creation and destruction are two faces of the same cosmic cycle. And so the coldest places are not barren voids but crucibles where the universe's next chapter is written, where gravity, radiation, and chemistry conspire to set the conditions for what comes next. If we could travel to the Boomerang Nebula, we would not find silence so much as a very slow kind of music, molecules colliding at glacial speeds, photons whispering their presence in faint microwave tones, a symphony of stillness. This poetic vision is supported by hard data because astronomers have measured line widths and Doppler shifts that tell us just how slowly this gas is moving, just how much heat has been drained from it into the background of space. The The background itself, the cosmic microwave background discovered by Arno Penzias and Robert Wilson in 1965, is the cold floor of the universe, a relic of the Big Bang that sets the baseline temperature for nearly everything we observe. At 2.7 Kelvin, the CMB is already unimaginably cold, yet the Boomerang Nebula manages to drop even lower by using its expanding gas as a natural refrigerator, converting heat into work as it cools. This process, called adiabatic expansion, is well known in thermodynamics, the same principle that causes the air from a spray can to feel cold as it escapes. But here it is playing out on scales trillions of times larger. To think that the same equations we use in a classroom can describe a nebula thousands of light years away is one of the triumphs of theoretical physics, connecting the human mind to the cosmos through mathematics. And yet, even as we find such order, there is a humbling reminder that the universe still contains mysteries beyond our reach, because there may be colder, stranger places yet to be discovered, dark clouds so frigid they barely emit anything at all. Some of these clouds might be so faint they escape detection until new instruments are built, meaning that every decade may bring a new coldest place, a new record holder for nature's deepest chill. This is what makes the pursuit of cosmic cold exciting. It is not a solved problem but a frontier, a reminder that even in a universe billions of years old, there are still records to break, still unknowns to chart. The quest for the coldest place is more than a curiosity. It is an investigation into the limits of thermodynamics, the boundaries of motion, and the deepest possible state of matter, pushing both theory and experiment to their extremes. Cryogenic engineers spend years designing apparatuses capable of reaching temperatures measured in nanokelvin, fighting against every stray photon and vibration that might add heat to their delicate systems, creating some of the quietest laboratories on Earth. These devices often involve nested layers of insulation, magnetic traps, and laser cooling beams carefully tuned to take energy away from atoms, one fraction of a photon at a time. A technological ballet that is breathtaking in its precision. The first successful demonstration of laser cooling in the 1980s, pioneered by Stephen Chu, Claude Cohen-Tanuji, and William D. Phillips, opened the door to the entire field of ultra-cold atomic physics, showing that light could be used not just to see atoms but to slow them. Their work was so revolutionary that it earned them the Nobel Prize in Physics in 1997, cementing the idea that extreme cold is not just a natural phenomenon, but a laboratory tool for probing the most fundamental laws of the universe. It is a striking parallel that as scientists on Earth reached colder and colder temperatures, astronomers were simultaneously discovering naturally occurring regions in space that mirrored those conditions on scales far beyond anything humans could build. This parallelism is poetic, as if the universe itself is inviting us to look closer, to match our ingenuity to its grandeur, to see that the smallest lab and the largest nebula are part of the same physical story. Even more intriguingly, there are cosmic voids, enormous regions spanning tens of millions of light years where there are very few galaxies, very little matter, and temperatures that approach the baseline set by the cosmic microwave background. These voids are like the universe's great silences, providing a contrast to the crowded clusters and filaments where most galaxies live, and serving as natural laboratories for studying how gravity behaves on the largest scales. Some of the coldest spots in the CMB map itself correspond to these voids, such as the Eridanus supervoid, a massive underdense region whose chilling presence may even have subtle effects on the expansion rate of the universe. The discovery of such voids has forced cosmologists to refine their models, to ask whether these regions are mere statistical flukes or signs of something deeper, perhaps even hints of exotic physics like dark energy behaving in unexpected ways. Dark energy itself is one of the coldest mysteries we face, a form of energy that seems to permeate all of space yet resists direct detection, pushing galaxies apart faster and faster as if the universe were accelerating downhill. In a very real sense, the study of cosmic cold is the study of cosmic destiny, because temperature, expansion, and energy density all determine whether the universe will expand forever, slow to a halt, or collapse back upon itself someday. This is why cosmologists like Stephen Hawking and Sean Carroll have spent decades modeling the far future of the cosmos, calculating whether the heat-death scenario, a universe where everything eventually cools to near absolute zero, is inevitable. Such calculations paint a picture both haunting and beautiful. A cosmos where stars go dark, black holes evaporate over unimaginable timescales, and only a thin bath of cold radiation remains as the final whisper of creation. But even this distant future may not be the final word, because quantum fluctuations and speculative theories like eternal inflation suggest that pockets of new universes might keep forming, keeping the cosmic story going forever. In this light, the coldest places we seek today might be just early hints of that ultimate stillness, previews of what the universe might one day become if expansion continues unchecked. For now, we keep building better detectors, better telescopes, and better cooling systems, pushing technology forward in our attempt to touch the very bottom of the temperature scale and listen to the faintest signals the cosmos has left for us. And so, Chapter 1 closes not with a final answer, but with an invitation to peer deeper into the void, to follow the trail of cold into Chapter 2, where we explore the hidden architecture of the universe and the strange physics waiting in the dark. As we step beyond the Boomerang Nebula and the frigid cradles of dying stars, we enter the vast empty expanses known as cosmic voids, regions that stretch for tens of millions of light years, where galaxies are scarce and the density of matter falls far below the cosmic average. These voids are not mere gaps in the cosmic landscape, but critical components of the large-scale structure of the universe, shaping the intricate web of filaments and clusters that define the distribution of matter across billions of light years. Within the sparse environment of these voids, temperatures approach the floor set by the cosmic microwave background, creating some of the coldest natural conditions in the observable universe, and a laboratory for understanding how matter behaves when it is nearly absent. Cosmologists such as Michael Vogel and R. Brent Tully have meticulously mapped these regions using galaxy surveys like the Sloan Digital Sky Survey, revealing the intricate network of filaments and nodes surrounding the vast emptiness. By studying the dynamics of galaxies at the edges of voids, researchers can infer how gravity, dark matter, and dark energy interact on the largest scales, offering insights into phenomena that would be impossible to replicate in terrestrial laboratories. Interestingly, some of these voids exhibit slight temperature differences in the cosmic microwave background, suggesting that photons passing through them lose energy via the integrated Sachs-Wolf effect, an imprint of dark energy on the cosmic fabric. This subtle cooling effect, measured using sensitive microwave telescopes, demonstrates that even vast regions of apparent emptiness are not uniform, but exhibit complex interactions that influence the evolution of the universe. Beyond voids, the universe's large-scale web is populated with cold molecular clouds, dense accumulations of gas and dust where star formation can occur under extremely low temperatures, typically ranging from 10 to 50 Kelvin. Within these clouds, chemistry continues at a glacial pace, allowing the formation of complex organic molecules such as methanol, formaldehyde, and even simple amino acids, providing the raw ingredients for life before they are incorporated into new stars and planetary systems. Observations using the Herschel Space Observatory in ALMA have revealed filamentary structures within these clouds, showing that gravity, turbulence, and magnetic fields work in concert to shape the distribution of matter at scales of several light years. In some of the coldest cores of these clouds, called pre-stellar cores, temperatures can drop below 10 Kelvin, and the density of matter increases to the point where hydrogen molecules begin to collapse under gravity, initiating the first stages of star formation. The interplay of cooling, pressure, and gravitational forces is a delicate balance, studied in detail by theorists such as Shuichiro Inusuka and Francesco Palla, who have modeled the conditions under which gas clouds fragment to form clusters of stars. This cold chemistry is not limited to simple molecules. Researchers have detected complex carbon chains and even prebiotic compounds, suggesting that the seeds of life may be sown in the icy darkness long before planets emerge. Even the shadowed craters of moons and planets within our own solar system echo this theme, harboring regions where temperatures are cold enough to preserve volatile ices for billions of years, offering potential resources for future human exploration. NASA's Lunar Reconnaissance Orbiter has mapped these permanently shadowed regions with unprecedented precision, revealing not just water ice but also traces of other volatiles like carbon dioxide and ammonia, locked in near perpetual cold. These extreme environments serve as natural laboratories for testing models of thermal evolution, radiation shielding, and the long-term stability of molecules under near absolute zero conditions, informing both planetary science and astrobiology. Meanwhile, experiments aboard the International Space Station, such as the Cold Atom Lab, complement these cosmic studies by producing Bose-Einstein condensates and ultra-cold gases in microgravity, revealing quantum phenomena that mirror processes occurring in the universe's coldest reaches. The insights gained from these studies have profound implications, demonstrating that extreme cold is not merely a passive state, but an active participant in shaping matter, chemistry, and potentially even life itself. In this way, the search for the coldest regions of the universe is simultaneously a journey inward toward the fundamental laws of physics and outward toward the vast empty expanses where matter is sparse and energy is minimal. As we chart these voids, clouds, and shadowed craters, a pattern emerges. Cold is a sculptor, a preserver, and an architect of cosmic evolution, influencing everything from the birth of stars to the survival of molecules that may one day seed life on new worlds. In exploring these cosmic cold zones, one encounters not only voids and molecular clouds, but also dwarf galaxies that drift on the outskirts of larger clusters, their low mass and sparse star formation making them exceptionally cold and dim. These galaxies, studied extensively by astronomers like Vera Rubin and Sandra Faber, reveal that coldness in the universe often accompanies low-energy activity, where gravitational interactions are slow and internal dynamics unfold over billions of years. Interestingly, the dark matter halos surrounding these dwarf galaxies exert subtle influences, shepherding gas and stars into specific configurations while preserving the overall cold, quiescent state of the system. These low-temperature environments also facilitate the survival of fragile molecules, which might otherwise be destroyed by stellar radiation in hotter, more active galaxies, hinting that cold may be a prerequisite for certain types of chemical evolution. Moving beyond galaxies, the cosmic web itself, composed of filaments of dark matter and gas connecting massive clusters, contains regions where gas temperatures drop dramatically, particularly in filaments far from energetic galaxies. Simulations by researchers such as Volker Springel and Lars Hernquist show that these filaments act as channels for matter to flow slowly into clusters, with the gas cooling adiabatically as it travels along gravitational potential wells. Within these frigid filaments, the density is low enough that collisions between atoms are infrequent, allowing temperatures to remain tens of millions of degrees colder than nearby galactic environments despite being immersed in the hot intergalactic medium. Remarkably, the physics governing these cold filaments mirrors laboratory phenomena such as ultra-cold plasma experiments, where low densities and slow particle velocities reveal quantum and hydrodynamic effects otherwise masked at higher temperatures. Observational campaigns using the Planck satellite and the Chandra X-ray Observatory have identified these tenuous structures through faint emissions in X-ray and microwave bands, confirming that even the universe's emptiest regions are structured and dynamic. Within these cold, low-density filaments, chemical processes proceed over extraordinary timescales, sometimes spanning hundreds of millions of years, allowing for the gradual formation of molecular clouds and the potential seeding of future star-forming regions. The interplay between cold and gravity in these environments is subtle. While low temperatures slow down atomic motion, gravitational attraction eventually dominates, leading to the gradual condensation of gas into denser clumps capable of igniting star formation. This gradual collapse demonstrates that cold is not a passive state but an active participant in cosmic evolution, regulating the pace at which matter assembles into structures ranging from stars to galaxies. Even at the scale of entire galaxy clusters, cold pockets exist, particularly in regions shielded from the energetic emissions of active galactic nuclei, allowing the intra-cluster medium to maintain temperatures far below what might be expected in such massive systems. These observations challenge our understanding of thermal balance on large scales, revealing that cold and hot regions coexist in a delicate equilibrium, with cooling flows slowly transporting gas inward while feedback from supermassive black holes injects heat. The contrast between the hot cores of clusters and their cooler peripheries illustrates that temperature is not uniform across the universe, but varies widely depending on local conditions, energy input, and cosmic history. Moving even further afield, the study of cosmic microwave background anomalies hints at ancient cold spots imprinted in the earliest moments after the Big Bang, relics of density fluctuations that have evolved over 13.8 billion years. Some of these primordial cold regions may correspond to supervoids in the modern universe, where matter is underdense, gravitational attraction is minimal, and temperatures remain close to the universal background floor. By combining observations across electromagnetic spectra, from radio to X-ray, astronomers can reconstruct the three-dimensional distribution of cold matter, revealing the hidden architecture of the cosmos and the intricate connections between its visible and invisible components. This grand design emphasizes that coldness is not merely a local phenomenon, but a structural feature of the universe, guiding the flow of matter and energy on the largest scales imaginable. As Chapter 2 progresses, we will examine how the combination of dark matter, cosmic expansion, and cooling processes produces the striking patterns observed in large-scale surveys, from filamentary networks to isolated cold voids. While cold voids and filaments dominate the large-scale structure of the universe, dark matter plays an equally crucial role in shaping the thermal and dynamic state of cosmic matter, acting as an invisible scaffold that guides the flow of baryonic gas into cold, dense regions. Simulations of galaxy formation, pioneered by researchers such as Simon White and Martin Rees, have shown that without the gravitational influence of dark matter, cold molecular clouds would be far less likely to coalesce, delaying star formation and altering the evolution of galaxies. In fact, many of the coldest regions observed in clusters and filaments correspond to the peaks of dark matter density, where the potential wells allow gas to cool efficiently while avoiding disruptive heating from nearby active galaxies or supernova feedback. This coupling between dark matter and baryonic matter demonstrates that extreme cold is often a byproduct of large-scale gravitational architecture, revealing that temperature is not simply a local property, but a reflection of cosmic structure. In galaxy clusters, cooling flows illustrate this principle beautifully. Gas in the central regions radiates away energy, gradually sinking deeper into the cluster potential well, forming cold cores where temperatures drop far below the surrounding hot intracluster medium. Observations from Chandra and XMM Newton have revealed that these cold cores often harbor reservoirs of molecular gas, sometimes containing tens of millions of solar masses, which can serve as the raw material for future star formation or accretion onto the central supermassive black hole. Intriguingly, the competition between cooling and heating processes determines whether a cluster remains quiescent or becomes dynamically active, illustrating that coldness is never absolute, but rather a balance of forces operating over vast scales. Even individual galaxies exhibit cold regions, such as the extended halos of atomic hydrogen surrounding spirals, which maintain temperatures just above the cosmic background, forming reservoirs that feed star formation over billions of years. Within these halos, gas can condense into high-velocity clouds plummeting towards the galactic disk under gravity, while maintaining temperatures low enough to allow molecules to survive the descent, creating localized pockets of extreme cold. Star-forming regions in galaxies are similarly governed by low-temperature physics. Dense cores within molecular clouds collapse under gravity, their low kinetic energy enabling the accumulation of mass without being disrupted by thermal pressure. These regions are natural laboratories for astrochemistry, where reactions occur at temperatures of just a few tens of Kelvin, allowing hydrogen to combine with carbon, oxygen, and nitrogen in unique pathways that are impossible in warmer environments. Telescopes such as ALMA have detected complex organic molecules in these cold cores, including methanol, formaldehyde, and even precursors to amino acids, suggesting that the universe's frigid pockets may play a critical role in seeding the chemical ingredients of life. Interestingly, the presence of cold dust in these regions helps shield fragile molecules from destructive ultraviolet radiation, allowing them to accumulate and persist long enough to be incorporated into nascent planets and protoplanetary disks. Even within our own solar system, cold regions preserve volatile ices that would otherwise evaporate, such as water in permanently shadowed lunar craters or carbon dioxide and methane ices on the surfaces of outer solar system moons. These regions serve as time capsules, maintaining primordial materials in a frozen state for billions of years, providing scientists with clues about the early chemical composition of the solar system and the conditions that may have led to life on Earth. Furthermore, the study of extreme cold extends beyond naturally occurring systems, as physicists on Earth recreate ultra-cold environments using laser cooling and magnetic traps to probe quantum mechanics in ways that parallel the slow dynamics of cosmic matter. Experiments aboard the International Space Station's Cold Atom Lab have allowed Bose-Einstein condensates to form in microgravity, extending observation times and enabling precision measurements that would be impossible on Earth, connecting the laboratory cold to cosmic cold in an elegant symmetry. By studying matter at near absolute zero, scientists can investigate quantum phenomena such as superfluidity, coherence, and entanglement, shedding light on the fundamental rules that govern particles in the universe's coldest regions. These insights inform our understanding of cosmic cold because the same physical laws apply whether the temperature is a fraction of a Kelvin in a lab or just a few degrees above absolute zero in the heart of a molecular cloud. Ultimately, the exploration of cold matter at all scales, from voids spanning millions of light years to ultra-cold atoms in orbit, reveals that low temperatures are not merely the absence of heat, but a dynamic facilitator of structure, chemistry, and evolution. As we move forward in this chapter, we begin to see how the interplay between cold, gravity, and chemistry underpins the emergence of stars, planets, and potentially habitable environments, highlighting the hidden architecture that governs the universe at every level. Within the cold cores of molecular clouds, the interplay of gravity, turbulence, and magnetic fields determines whether a clump of gas will collapse into a star or dissipate harmlessly into the surrounding medium, a delicate balance studied by theorists such as Christopher McKee and Eve Ostriker. These ultra-cold environments allow gas to fragment into filaments only a few light-years long, each potentially forming multiple stellar embryos that will grow over millions of years, their evolution governed by the initial conditions set by the cold, dense medium. The temperature in these regions can fall below 10 Kelvin, low enough that molecular hydrogen, the universe's most abundant element, behaves differently than in warmer conditions, facilitating chemical reactions that would otherwise be too slow to occur. Observations using millimeter-wave telescopes reveal a wealth of molecular species, including carbon monoxide, ammonia, and formaldehyde, mapping the chemical richness that cold enables and providing a glimpse into the primordial chemistry of galaxies. As gas collapses into protostellar cores, the surrounding cold envelope acts as both a shield and a reservoir, slowing down the dispersal of heat and allowing matter to accrete steadily onto the forming star, a process first modeled by theorists like Frank Hsu. Meanwhile, cold dust grains within these clouds serve as catalytic surfaces for chemical reactions, enabling the formation of complex organics and even prebiotic molecules, demonstrating that low temperatures can foster chemical diversity critical for life. These chemical factories operate on timescales of millions of years, their slow reactions allowing unusual molecular structures to form and persist in conditions that would rapidly destroy them in warmer regions of space. Interestingly, some regions within cold molecular clouds contain turbulence that paradoxically supports both stability and fragmentation, creating pockets where stars can form while neighboring gas remains quiescent, illustrating the complex physics at play in ultra-cold environments. Protostars themselves emit radiation, slowly heating their surroundings, but the cold outer layers of the cloud continue to regulate the overall temperature, ensuring that the process of star formation is both efficient and gradual. Meanwhile, in the dense cores, molecular chemistry continues, producing ions, radicals, and complex carbon chains, some of which may eventually be incorporated into planetary systems, hinting at the connection between cosmic cold and the origins of organic matter. Cold temperatures also slow the motion of dust grains, allowing them to coagulate and form larger particles, the first steps toward planet formation in protoplanetary disks, highlighting that ultra-cold environments are critical not only for stars but for worlds. Observations of nearby star-forming regions such as the Taurus molecular cloud and the Orion Nebula reveal that these processes are not hypothetical but actively occurring, with dense cold cores producing protostars at different evolutionary stages. Even in the outer reaches of our own solar system, in the Kuiper Belt and Oort cloud, temperatures remain near 30-50 Kelvin, preserving ices and frozen volatiles that provide insight into the conditions from which the planets formed. These ultra-cold regions serve as laboratories for planetary scientists and astrochemists alike, offering a window into how temperature controls the physical and chemical evolution of matter over billions of years. Beyond star and planet formation, cold gas plays a critical role in galaxy evolution, as low-temperature filaments feed galaxies with fresh material, regulate star formation rates, and shape the morphology of galactic disks over cosmological timescales. This process is influenced by feedback from supernovae and active galactic nuclei, which inject energy and heat into the surrounding medium. But cold regions remain protected or rapidly reform, illustrating the resilience of ultra-cold structures. Remarkably, even in high-density environments like galactic centers, cold molecular gas can survive in shielded pockets, demonstrating that extreme cold is not confined to the outer universe, but can coexist with energetic processes in complex interplay. The combination of cold chemistry, low-density gas dynamics, and gravitational shaping leads to emergent structures that are simultaneously beautiful and scientifically revealing, from filamentary clouds to globular clusters, each shaped by the universe's cold hand. Cold also plays a role in regulating the initial mass function of stars, influencing whether a molecular cloud produces many small stars or a few massive ones, an area of ongoing research that connects temperature directly to cosmic demographics. In this way, the study of cold matter unifies multiple scales of astronomy, from the microphysics of molecular reactions to the macroscopic evolution of galaxies, revealing the hidden architecture that underpins the cosmos. It is an active agent, sculpting matter, regulating chemistry, and enabling the slow emergence of complexity across the universe. As we venture deeper into the coldest reaches of the universe, attention turns to the dense cores of galactic filaments, where temperatures hover just above absolute zero, and matter slowly accumulates under the influence of gravity and magnetic fields. These ultra-cold cores, often observed in infrared and millimeter wavelengths, provide ideal laboratory for studying the earlier stages of star and planet formation, revealing how low temperatures govern the pace and pathways of cosmic evolution. Within these cores, molecular hydrogen dominates, but trace molecules such as carbon monoxide, ammonia, and formaldehyde act as critical tracers, allowing astronomers to map density, temperature, and kinematics with exquisite precision. The presence of dust grains, frozen solid at temperatures of 10 Kelvin or lower, enables complex chemical reactions, serving as catalytic surfaces where molecules combine, fragment, and sometimes form prebiotic compounds that may eventually seed planetary systems. Observatories like ALMA, the VLA, and SOFIA have revealed that these cold cores are highly structured, with filaments twisting and intersecting, forming nodes of enhanced density that are the birthplaces of future stars and stellar clusters. Interestingly, even within the same filament, temperature variations of just a few Kelvin can dramatically alter the chemical pathways, favoring the formation of certain molecules over others and highlighting the sensitivity of cosmic chemistry to ultra-cold conditions. As gas continues to collapse under gravity, protostellar cores emerge, surrounded by disks of cold dust and gas that rotate slowly, feeding the central condensation while maintaining the low temperatures necessary for continued chemical activity. Magnetic fields threading through these regions act as regulators, channeling infall and preventing catastrophic fragmentation, illustrating how cold, gravity, and magnetism cooperate to shape the architecture of nascent stellar systems. The ultra-cold environment also enables the survival of fragile molecules that would otherwise be destroyed by radiation, such as water, methanol, and complex organics, preserving the raw ingredients necessary for potential habitability in later planetary systems. Even as protostars ignite and begin to heat their immediate surroundings, the surrounding envelope remains cold, ensuring that chemical synthesis continues, and that the outer regions retain the conditions necessary for further collapse or secondary star formation. In galaxy clusters, similar cold filaments feed the central galaxies, providing a steady inflow of molecular gas that is critical for maintaining star formation over cosmological timescales, despite the energetic feedback from supernovae and active nuclei. These cooling flows, first hypothesized in the 1970s and later confirmed by X-ray observations, demonstrate that cold is not simply a passive byproduct but an active mechanism shaping galactic evolution and regulating star formation rates. Moreover, the interaction between cold gas and hot plasma in cluster environments leads to intricate dynamics, including shocks, turbulence, and mixing layers, where temperature gradients produce localized pockets of extreme cold within otherwise warm regions. These pockets of extreme cold serve as incubators for molecular formation, sometimes generating unexpected chemical complexity that challenges models of astrophysical chemistry and suggests that ultra-cold conditions are essential for the universe's molecular diversity. Interestingly, observations of cold cores in nearby clusters like Perseus and Virgo have revealed that molecular filaments can extend over tens of thousands of light-years, surviving in frigid equilibrium against the ambient hot intracluster medium. Within these long cold filaments, star formation can proceed in localized nodes while the majority of the gas remains inert and near absolute zero, demonstrating the patchwork nature of cold in the universe and its role in regulating cosmic structure. Even in regions affected by supernova remnants, pockets of cold gas can persist, shielded by dust and magnetic fields, suggesting that ultra-cold environments are remarkably resilient and capable of maintaining their chemical and physical integrity over millions of years. The connection between cosmic cold and the origins of life becomes apparent when considering that these dense, ultra-cold regions provide stable environments where prebiotic molecules can form, accumulate, and survive long enough to be incorporated into emerging planetary systems. Laboratory experiments on Earth mirror these conditions, with ultra-cold chemistry and magnetic and optical traps reproducing reactions that occur in space, demonstrating that cold is not merely a backdrop but a driving force for molecular complexity. Finally, as we conclude Chapter 2, the tapestry of cosmic cold reveals itself as both subtle and profound, linking the formation of stars, galaxies, and molecular structures with the potential for life, highlighting that cold is an architect, sculptor, and preserver within the grand design of the universe. The next chapter will take us further, exploring the coldest known laboratory in the universe, the Boomerang Nebula, and investigating why its temperature is lower than any other naturally occurring region, setting the stage for the ultimate extremes of frigid cosmic environments. Welcome to the realm of cosmic extremes, where the universe reveals that cold is not merely the absence of heat, but a dynamic force capable of sculpting matter, regulating chemistry, and even dictating the evolution of stars and galaxies across billions of light years. In the southern constellation of Centaurus, astronomers discovered an extraordinary object whose temperature defies common intuition, the Boomerang Nebula, a pre-planetary nebula whose frigid gas measures a mere 1 Kelvin, colder than the background radiation of space itself. This discovery, first reported by Raghavendra Sahai and collaborators using millimeter wave observations, challenged conventional understanding of cosmic thermodynamics and inspired new inquiries into how nature can achieve temperatures colder than the cosmic microwave background. The nebula itself is the ejected envelope of an aging star, expanding outward at supersonic speeds, and in doing so, the gas undergoes rapid adiabatic cooling, a process in which expansion converts internal energy into work, lowering the temperature to unprecedented lows. Inside this ultra-cold envelope, molecules such as carbon monoxide remain stable, serving as tracers for astronomers to map the density, velocity, and temperature gradients, revealing a remarkably structured but frigid environment. The Boomerang Nebula's extreme cold is not accidental. It results from a combination of stellar mass loss, rapid expansion, and radiative cooling, a delicate balance that allows the gas to reach temperatures lower than any other known naturally occurring region in the universe. Observations using instruments like the Atacama Large Millimeter Submillimeter Array ALMA have provided exquisite detail of the nebula's structure, revealing filamentary streams of cold gas and asymmetries that hint at binary interactions in the progenitor system. These findings illustrate that even in the coldest regions, complexity persists, with turbulence, rotation, and small-scale density variations producing a rich landscape of physical conditions, all occurring at temperatures barely above absolute zero. Interestingly, the Boomerang Nebula demonstrates that cooling can be more extreme in low-density gas than in dense molecular clouds, as collisions between particles are rare, and expansion allows energy to dissipate efficiently into the void of space. The study of this nebula has implications beyond a single object, providing a natural laboratory for understanding cooling mechanisms in other environments, such as supernova remnants, planetary nebulae, and even interstellar filaments where low temperatures dominate the chemistry. By comparing observational data with theoretical models, scientists like Sahai and Neiman have been able to reconstruct the history of mass ejection, expansion velocities, and temperature evolution, shedding light on how a star nearing the end of its life can create the coldest known pockets in the cosmos. These insights reveal that cold is not merely a passive outcome but an active participant, shaping the distribution of matter and guiding chemical processes that might otherwise be overwhelmed by heat and radiation in more energetic environments. The Boomerang Nebula also serves as a bridge in understanding extreme physics, linking terrestrial laboratory studies of ultra-cold atoms to cosmic phenomena, as both systems highlight how matter behaves when energy is minimized and quantum effects can become significant. Astronomers continue to probe the nebula's outer regions, where the gas is expanding into the surrounding interstellar medium, creating shock fronts and interactions that, despite the low temperature, reveal dynamic behavior and intricate structures at enormous scales. Even in its extreme cold, the Boomerang Nebula is influenced by stellar radiation, cosmic rays, and magnetic fields, demonstrating that no environment is entirely isolated, and that ultra-cold conditions exist within a delicate balance of competing forces. The discovery and study of such cold extremes challenge our assumptions about the universe, forcing scientists to reconsider the mechanisms by which energy is transported, matter cools, and molecules survive in regions far removed from the warmth of stars. Moreover, the nebula provides a vivid example of how temperature can govern chemical evolution, as ultra-cold conditions preserve molecules and enable reactions that are impossible in warmer regions, bridging the fields of astrochemistry, stellar evolution, and observational astronomy. In this sense, the Boomerang Nebula is not simply the coldest place in the universe by measurement. It is a natural experiment demonstrating the profound effects of temperature on structure, chemistry, and dynamics in astrophysical systems. Finally, understanding why this nebula reaches such extreme temperatures illuminates broader questions about the coldest corners of the cosmos, guiding searches for other ultra-cold objects, and refining our models of how stars interact with their environments at the end of their lifetimes. The Boomerang Nebula's molecular composition is dominated by carbon monoxide, a stable molecule that emits in millimeter wavelengths, making it an ideal tracer for astronomers to measure temperature, density, and velocity within the ultra-cold envelope. Additional molecules, including hydrogen cyanide, formaldehyde, and even traces of more complex organics, have been detected, revealing that chemical activity persists despite temperatures barely above 1 Kelvin, providing a natural laboratory for extreme astrochemistry. These molecular observations are made possible by sensitive instruments like ALMA and the submillimeter array, which can detect faint emissions that reveal the distribution of gas, the velocity of expansion, and the intricate structure of the nebula's outflow. The nebula's extreme cold arises largely from adiabatic expansion, a process in which gas ejected from the progenitor star expands so rapidly that its internal energy drops, cooling the material to temperatures lower than even the surrounding cosmic microwave background. This expansion occurs at velocities exceeding 164 kilometers per second, stretching the gas over a distance of more than a light year while maintaining a remarkably uniform temperature profile, as confirmed by millimeter wave spectral observations. Interestingly, the Boomerang Nebula demonstrates that density and expansion are critical in determining how low temperatures can reach, as low-density gas cools more efficiently than dense molecular clouds due to fewer collisions between particles. The outer layers of the nebula, moving fastest, reach temperatures barely above 1 Kelvin, while inner layers are slightly warmer, producing a temperature gradient that offers insight into the physics of stellar mass loss and wind dynamics in dying stars. Sahai and colleagues have modeled this process extensively, showing that binary interactions may influence the shape of the nebula, producing its characteristic hourglass morphology, and that the coldest regions coincide with the fastest expanding, lowest density gas. This combination of observational and theoretical work highlights how ultra-cold environments are shaped by multiple factors, including stellar evolution, kinematics, chemical composition, and radiative processes, all converging to produce a natural extremum of temperature. The nebula's extreme cold has implications for the survival of molecules and dust grains, as low temperatures reduce kinetic energy and collisions, allowing fragile compounds to persist over tens of thousands of years and possibly contribute to the chemical evolution of the interstellar medium. Moreover, the Boomerang Nebula's chemical composition provides a window into the late stages of stellar evolution, particularly the asymptotic giant branch phase, when stars shed mass at prodigious rates, enriching the surrounding space with cold molecular material. The study of radiative cooling in this nebula also sheds light on fundamental physics, as photons emitted by molecules carry away energy, allowing gas to reach temperatures lower than the ambient cosmic microwave background, a counterintuitive but well understood process. These ultra-cold conditions enable astrochemists to explore reactions that are impossible at higher temperatures, where thermal energy would break chemical bonds, highlighting that cold is not merely passive but actively governs molecular pathways in space. The outer envelope of the Boomerang Nebula, stretching over vast distances, is particularly instructive, as it demonstrates how low-density gas can remain ultra-cold while expanding into the interstellar medium, contrasting sharply with warmer, denser, star-forming clouds elsewhere. ALMA's high-resolution imaging reveals fine filaments and clumps within the nebula, suggesting that even in the coldest regions, local variations in density and turbulence can create pockets of chemical richness, offering clues about the conditions under which molecules form and survive. The Boomerang Nebula also exemplifies how extreme environments inform our understanding of universal processes, from thermodynamics to fluid dynamics, as adiabatic cooling, radiative loss, and expansion converge to produce temperatures lower than any other naturally occurring region. Interestingly, laboratory studies of ultra-cold gases on Earth using techniques like laser cooling and magnetic trapping echo some of the physical principles observed in the nebula, demonstrating that whether in a lab or across light years of space, low-temperature physics behaves consistently under the laws of nature. Finally, the Boomerang Nebula challenges our intuition, teaching us that the coldest corners of the cosmos are not found in the voids between galaxies or in distant molecular clouds, but can emerge from the violent, expanding envelopes of dying stars, where nature orchestrates an extraordinary balance of expansion, radiation, and chemistry. The physics of adiabatic cooling in the Boomerang Nebula demonstrates that as gas expands rapidly into the surrounding vacuum, its internal energy is converted into work, effectively reducing the temperature to levels that defy conventional expectations of cosmic thermodynamics. This process, governed by the ideal gas law and principles of fluid dynamics, is accelerated by the high velocity of the outflowing material, which can exceed 160 kilometers per second, stretching the gas over light-year scales while maintaining its ultra-cold state. Temperature gradients within the nebula are subtle but measurable, with the outermost layers reaching the lowest temperatures while inner layers remain slightly warmer, allowing astronomers to reconstruct the thermal history and expansion dynamics of the ejected material. Molecular traces such as carbon monoxide and hydrogen cyanide are critical in this analysis, as their rotational transitions emit in millimeter wavelengths, providing precise measurements of density, velocity, and local temperature that illuminate the structure of the nebula. High-resolution spectroscopy reveals that even within the coldest regions, localized turbulence and small-scale variations exist, hinting at complex interactions between gravity, magnetic fields, and radiation that subtly shape the distribution of gas. Interestingly, the survival of molecules in such extreme cold is facilitated by the low kinetic energy of particles, which prevents destructive collisions and allows fragile chemical bonds to persist over tens of thousands of years, far longer than in warmer environments. The cold also stabilizes dust grains, which act as catalytic surfaces for the formation of more complex molecules, enabling the synthesis of organics that would otherwise be destroyed by thermal agitation in hotter regions of space. Radiative processes, including the emission of photons from molecules like CO, provide a pathway for energy to escape the gas, reinforcing the cooling effect and maintaining the nebula at temperatures below the cosmic microwave background, an unusual but well understood phenomenon. The interplay between adiabatic expansion and radiative cooling illustrates that ultra-cold environments are not static but dynamic, with energy continuously redistributed, shaping the temperature, density, and chemical composition of the gas. Observational campaigns using ALMA and the submillimeter array have mapped these gradients in exquisite detail, revealing filamentary structures, clumps, and asymmetries that hint at past stellar activity and the influence of binary interactions in the progenitor system. These observations also show that the coldest regions are not uniform. Small pockets of slightly warmer gas exist, influenced by shocks, turbulence, and residual stellar radiation, demonstrating the complex microphysics operating even in environments near absolute zero. The survival of molecules in the ultra-cold gas depends not only on temperature but also on shielding by dust and self-shielding effects, which protect the molecular species from ultraviolet radiation that would otherwise dissociate them. Studies of isotopic ratios within these molecules provide further insight into the origin and evolution of the nebula, revealing evidence of nuclear processing in the progenitor star and enrichment of the ejected material with heavy elements. Interestingly, the Boomerang Nebula exemplifies how extreme cold can regulate chemistry in ways that are both predictable and surprising, allowing reactions to occur at glacially slow rates yet producing molecules that are essential to interstellar chemistry and potentially prebiotic processes. The nebula's expansion velocity and ultra-cold state also permit the formation of filamentary substructures, where gas density variations create pockets of enhanced molecular richness, suggesting that even in frigid conditions, complex chemical environments can arise naturally. Observations of these filaments show that they can extend thousands of astronomical units, maintaining coherence and cold temperatures over vast distances, offering a rare glimpse into the mechanisms that preserve ultra-cold gas in a dynamic, expanding medium. The combination of expansion, radiative loss, and shielding creates a self-regulating system in which the coldest regions persist, molecules survive, and dust grains remain intact, demonstrating that ultra-cold environments can be stable over astronomical timescales. Finally, the Boomerang Nebula serves as a cosmic benchmark, illustrating the lower limits of temperature achievable in nature and providing astronomers with a template for identifying other ultra-cold objects from preplanetary nebulae to diffuse interstellar clouds. Within the ultra-cold reaches of the Boomerang Nebula, molecular mapping has revealed a surprisingly rich chemistry, with carbon monoxide, formaldehyde, hydrogen cyanide, and even trace organic compounds distributed throughout the expanding envelope, each molecule providing clues to the nebula's physical and chemical history. These molecules survive despite the extreme temperatures because the kinetic energy of particles is so low that collisions rarely break chemical bonds, allowing fragile compounds to persist for tens of thousands of years and maintain a record of the progenitor star's evolution. Dust grains embedded in the gas serve as catalytic surfaces, where molecules can stick, react, and form more complex species, demonstrating that even in near absolute zero conditions, chemical complexity can emerge naturally from simple ingredients. The low temperatures slow reaction rates, meaning that processes that would be nearly instantaneous in warmer regions occur over thousands or millions of years, creating an environment where unusual molecular structures can form and persist. Astronomers using ALMA have traced these molecules to specific regions within the nebula, revealing filaments, clumps, and asymmetrical structures that suggest turbulence, shocks, and local density variations play a role even in the coldest zones. Observations indicate that some molecules are concentrated near the fastest expanding gas, hinting at a connection between kinematics and chemistry, where adiabatic cooling not only lowers temperature but also stabilizes certain molecular species. Interestingly, the ultra-cold conditions preserve molecular isotopic ratios, allowing astronomers to study nucleosynthesis in the progenitor star and trace the chemical evolution of the ejected material over time, linking cold chemistry to stellar life cycles. The persistence of carbon-based molecules in such frigid environments raises intriguing questions about the potential for prebiotic chemistry, as these compounds form the building blocks for amino acids and other biologically relevant molecules, long before planets exist. Dust grains coated with icy mantles act as sites for surface reactions, where simple molecules like CO and H2O can combine to create more complex organics, demonstrating that ultra-cold environments can facilitate chemistry critical to the origins of life. The Boomerang Nebula also illustrates how temperature gradients influence chemical pathways, as slightly warmer inner layers allow reactions that are suppressed in the coldest outer regions, producing spatial variation in molecular abundance and composition. Spectral line observations have revealed fine structure within these molecules, showing that even in extreme cold, rotational and vibrational transitions occur, providing astronomers with a wealth of data to reconstruct physical conditions within the nebula. These insights have implications for our understanding of interstellar chemistry, as they demonstrate that ultra-cold conditions do not inhibit molecular synthesis, but instead create unique pathways that are inaccessible at higher temperatures. The survival of fragile compounds in the Boomerang Nebula also informs models of molecular transport into the interstellar medium, suggesting that cold envelopes around dying stars may seed surrounding space with chemically rich material. Furthermore, dust grains shield molecules from ultraviolet radiation, providing additional protection and enabling reactions that require low temperatures and minimal disruption, highlighting the interplay between physical structure and chemical preservation. The detection of organic molecules in such extreme conditions demonstrates that the universe's chemical richness is not confined to warm, star-forming regions, but extends to the coldest corners, where slow, deliberate chemistry can produce complex species. Interestingly, ultra-cold dust and molecular environments serve as natural laboratories, allowing scientists to test models of astrochemical kinetics, molecular stability, and surface reactions under conditions impossible to reproduce fully on Earth. The implications extend to astrobiology, as the preservation and synthesis of organics in these frigid environments suggest that the building blocks of life can exist long before planets form, waiting for conditions suitable for further chemical evolution. Finally, the combination of adiabatic cooling, radiative processes, and dust-mediated chemistry in the Boomerang Nebula reveals a delicate balance in which ultra-cold conditions actively shape molecular complexity, highlighting that the coldest places in the universe are also the most chemically intriguing. In the Boomerang Nebula, dust grains play a crucial role in shaping the chemical landscape, acting as tiny catalysts where molecules adhere, interact, and form more complex compounds, even under temperatures barely above 1 Kelvin. These grains, often composed of silicates, carbonaceous material, and icy mantles, provide surfaces where simple molecules such as CO, H2O, and NH3 can combine, producing organics that may later contribute to the molecular diversity of the interstellar medium. Icy mantles form as gas phase molecules condense onto the surface of grains, creating layers that can harbor reactive species and enable surface chemistry that is otherwise inaccessible in the gas phase due to low densities and ultra-cold conditions. Laboratory simulations of these processes on Earth using cryogenic temperatures and vacuum chambers confirm that molecules can migrate across grain surfaces, react, and form new compounds, mirroring the chemistry observed in the Boomerang Nebula and other cold cosmic regions. Interestingly, some molecules formed on dust grains are fragile and would quickly dissociate at higher temperatures, but in the Boomerang Nebula, the ultra-cold environment allows them to persist, offering a natural archive of prebiotic chemical evolution. Radiation, including cosmic rays and residual stellar photons, interacts with these icy mantles, sometimes driving chemical reactions that produce more complex organics, while the low ambient temperature ensures that the products are not immediately destroyed. The interplay between shielding, ultra-cold conditions and radiation highlights a delicate balance, where chemistry proceeds slowly yet steadily, generating molecules that may eventually contribute to the raw materials for life in newly forming planetary systems. Observations using millimeter and sub-millimeter spectroscopy have mapped the distribution of these icy dust grains, showing that filaments and clumps can retain their ultra-cold state over thousands of astronomical units, maintaining stable surfaces for chemical reactions to continue. These grains also play a mechanical role, influencing the dynamics of the expanding envelope by coupling with the gas, transferring momentum, and regulating the overall expansion rate, which in turn affects how cold temperatures are maintained across the nebula. Interestingly, the formation of icy mantles is not uniform. Variations in local density, turbulence, and radiation produce heterogeneous coverage, creating microenvironments with slightly different chemical pathways and molecular abundances. Some of these microenvironments are shielded by larger dust structures, allowing extremely fragile molecules to survive in pockets where radiation penetration is minimal, effectively creating natural laboratories for studying ultra-cold chemistry. The survival of complex organics in these regions had been confirmed through rotational spectroscopy, which detects the faint emission lines of molecules frozen in icy mantles, providing a glimpse into the chemistry of a dying star's ejected material. These findings underscore the importance of ultra-cold environments as molecular preservers, where chemical diversity is maintained far longer than in warmer nebulae, allowing astronomers to trace the history of stellar ejecta and the evolution of molecular clouds. Dust grains in the Boomerang Nebula also contribute to the opacity of the envelope, controlling how radiation escapes and thereby indirectly influencing the thermal balance, expansion, and survival of molecules throughout the ultra-cold regions. The interplay of dust, gas, and radiation creates a self-regulating system where ultra-cold temperatures are maintained despite dynamic expansion, turbulence, and shocks, demonstrating that cold is an active factor in shaping both chemistry and structure. In addition to chemical implications, dust grains are essential for understanding the nebula's infrared emission, as they absorb stellar light and re-radiate it, allowing astronomers to probe the distribution, temperature, and composition of the cold envelope remotely. The Boomerang Nebula thus exemplifies how ultra-cold regions are not inert but dynamically rich, with dust grains serving as both chemical factories and regulators of energy, demonstrating the profound effects of cold on molecular evolution in space. These ultra-cold dust-mediated processes have implications for the enrichment of the interstellar medium, as molecules and organics preserved in the Boomerang Nebula may eventually mix with surrounding space, seeding future star-forming regions with chemically rich material. High-resolution spectroscopy has been a cornerstone in understanding the Boomerang Nebula, revealing the faint millimeter and submillimeter emissions of molecules embedded within the ultra-cold gas, allowing astronomers to map density, temperature, and velocity across its expanding envelope. Using instruments such as ALMA and the submillimeter array, researchers have detected rotational transitions of carbon monoxide, hydrogen cyanide, and other species, tracing the structure of the nebula down to scales of a few hundred astronomical units. Velocity mapping of these molecular lines has revealed complex dynamics within the ultra-cold gas, including supersonic expansion, localized turbulence, and subtle asymmetries that point to the influence of binary interactions and past stellar activity. Interestingly, the Boomerang Nebula's filaments and clumps maintain coherence despite their ultra-cold state, indicating that even at temperatures near 1 Kelvin, gas can flow, collide, and interact in ways that shape both the chemical and physical structure of the nebula. Spectral line broadening and Doppler shifts provide further insight into the kinematics of the envelope, showing that the fastest moving outer layers correspond to the coldest regions, consistent with adiabatic expansion cooling the gas as it accelerates outward. The interplay of cold gas, dust, and radiation creates a dynamic system in which energy is continuously redistributed, molecules are shielded from destruction, and ultra-cold conditions are maintained despite ongoing expansion and turbulence. ALMA observations have revealed that some molecular filaments are remarkably straight, suggesting that magnetic fields may guide the motion of gas and dust even in ultra-cold conditions, influencing both chemistry and large-scale structure. The detection of asymmetries and clumps also indicates that the nebula is not a smooth, isotropic envelope, but a heterogeneous environment where density variations, turbulence, and shocks all contribute to chemical diversity and structural complexity. Velocity gradients mapped across the nebula allow astronomers to reconstruct the history of mass ejection from the progenitor star, revealing how the timing, speed, and direction of expelled material affect the formation of ultra-cold regions and chemical distribution. Interestingly, radiation from the central star is largely absorbed or scattered by dust, minimizing heating of the outer envelope and enabling the gas to remain at ultra-cold temperatures, demonstrating how physical shielding contributes to chemical preservation. These observational breakthroughs have allowed scientists to model the interactions between cold gas, dust grains, and radiation, illustrating that even in extreme low-temperature environments, the balance of forces dictates the survival and distribution of molecules. The Boomerang Nebula is not unique in its ultra-cold characteristics. Comparisons with other preplanetary nebulae and diffuse molecular clouds reveal that extreme cooling is most effective in low-density, rapidly expanding envelopes where adiabatic processes dominate over radiative heating. Filamentary dynamics, observed through Doppler mapping and spectral analysis, show that even at temperatures near 1 Kelvin, gas flows along preferred directions, guided by magnetic fields, pressure gradients, and the legacy of stellar winds from the progenitor star. The preservation of molecules within these filaments is particularly striking, as slight variations in density or exposure to radiation can create microenvironments where chemical pathways diverge, allowing for the synthesis and survival of diverse species across the nebula. Interestingly, ultra-cold dust grains embedded within these filaments act as both shields and catalysts, mediating surface reactions that produce organics, while also absorbing radiation that might otherwise destroy fragile molecular bonds. These insights underscore that ultra-cold environments are not static but dynamic, with energy continually redistributed, chemical reactions proceeding slowly on icy grain surfaces, and filaments guiding the flow and survival of molecules across astronomical scales. ALMA and other high-resolution observatories have confirmed that the coldest regions coincide with the fastest expanding gas, supporting theoretical predictions that adiabatic expansion in low-density envelopes can produce temperatures lower than the cosmic microwave background. Interestingly, these observations also reveal that ultra-cold gas and dust can maintain coherence over thousands of astronomical units, demonstrating that molecular and structural preservation is possible even in highly dynamic, low-density environments. The study of velocity mapping, spectroscopy, and filamentary dynamics in the Boomerang Nebula provides a comprehensive view of how ultra-cold environments function, illustrating the interplay between physics, chemistry, and radiation in shaping the coldest regions of the cosmos. The Boomerang Nebula demonstrates that the coldest regions in space emerge from a combination of rapid expansion, low-density gas, and radiative cooling, producing temperatures that challenge our conventional understanding of how cold a natural environment can become. Interactions between ultra-cold gas and dust grains create microenvironments where molecules can adhere to surfaces, react, and survive despite the low temperatures, allowing complex organics to persist in ways that would be impossible in warmer regions. Velocity gradients in the expanding envelope shape the distribution of gas and dust, producing filaments, clumps, and asymmetries that influence both chemical pathways and the physical structure of the nebula on scales ranging from hundreds of astronomical units to light years. Observations reveal that the fastest moving gas corresponds to the lowest temperatures, confirming theoretical models of adiabatic cooling and demonstrating how expansion can regulate thermal conditions across a vast ultra-cold region. Dust grains within the nebula not only act as catalysts for chemical reactions, but also provide shielding from ultraviolet and residual stellar radiation, preserving molecules that would otherwise be destroyed and enabling a slow buildup of chemical complexity. The distribution of icy mantles across grains varies with density, turbulence, and radiation exposure, creating pockets where reactions occur more efficiently and highlighting the sensitivity of ultra-cold chemistry to subtle physical differences within the nebula. Spectroscopic studies allow astronomers to detect faint rotational transitions of molecules, mapping their velocities, densities, and excitation states, and revealing the presence of chemical heterogeneity even in regions where temperatures are barely above absolute zero. Filamentary structures provide a framework for understanding how gas flows and organizes under ultra-cold conditions, as magnetic fields, pressure gradients, and residual stellar wind patterns guide the motion of both dust and gas across the expanding envelope. Turbulence within these filaments introduces localized variations in density and temperature, producing chemical niches where molecules can survive longer or form more complex compounds, demonstrating that even near 1 Kelvin, the environment is dynamic and structured. Adiabatic cooling ensures that the ultra-cold gas maintains stability as it expands, while radiative losses allow energy to escape efficiently, creating a feedback loop where chemistry, temperature, and motion are closely intertwined throughout the envelope. The Boomerang Nebula illustrates that ultra-cold chemistry is not limited by absolute temperatures, but is instead governed by the interplay between density, shielding, dust-mediated reactions, and slow, deliberate energy redistribution across the nebula. Regions of varying density produce subtle contrasts in molecular abundance, showing that even small differences in local conditions can influence the pathways of chemical reactions and the survival of fragile molecules over astronomical timescales. Observations suggest that as the ultra-cold gas merges with the surrounding interstellar medium, molecules and dust grains may be carried into larger clouds, seeding future star-forming regions with chemically rich material, linking the coldest corners of dying stars to the cycle of cosmic evolution. ALMA imaging reveals that filaments can extend across thousands of astronomical units while maintaining coherence, demonstrating that ultra-cold gas retains structural integrity despite the dynamic forces acting upon it, including turbulence, expansion, and radiation pressure. Icy dust mantles create surfaces for slow chemical synthesis, allowing molecules to migrate, react, and accumulate over long periods, highlighting that the universe's coldest regions are not barren, but are laboratories for molecular diversity in prebiotic chemistry. The Boomerang Nebula challenges traditional notions of where the coldest places in the cosmos might be, as it demonstrates that extreme cooling arises not in empty intergalactic voids but within the expanding low-density envelopes of dying stars shaped by the interplay of gas dynamics, radiation, and dust. Ultra-cold filaments and clumps preserve chemical signatures that may survive long enough to mix with other regions of the interstellar medium, implying that the material expelled by dying stars contributes actively to the chemical evolution of the galaxy. The combination of ultra-cold temperatures, dust-mediated chemistry, and dynamic expansion illustrates that cold is an active force in shaping molecular complexity, structural diversity, and the evolution of dying stars' envelopes into chemically rich material for the next generation of cosmic structures. The Boomerang Nebula provides a benchmark for understanding the limits of natural cooling, offering astronomers a window into the physics and chemistry of ultra-cold environments, while also revealing the unexpected richness and activity that can exist at the coldest extremes of the universe. Across the universe, ultra-cold regions exist in locations far beyond the Boomerang Nebula, where the delicate interplay of gas dynamics, radiation, and low densities produces temperatures that challenge the boundaries of what we consider possible in natural environments, revealing that the coldest places are not simply empty voids, but intricate laboratories of cosmic physics and chemistry. In diffuse molecular clouds, for example, temperatures can approach just a few degrees above absolute zero, maintained by the balance between radiative cooling and the infrequent collisions of sparse gas molecules, while shielding from starlight and cosmic rays preserves fragile chemical species that would otherwise break apart. The physics behind these extreme temperatures relies heavily on processes such as adiabatic expansion, where low-density gas moving into vacuum experiences a rapid drop in temperature, and radiative cooling, in which molecules emit photons that carry energy away from the system, reinforcing the ultra-cold conditions. Interstellar ice grains provide a further mechanism for sustaining chemical richness, acting as both protective shelters and catalytic surfaces, where simple molecules like CO, H2O, and NH3 can undergo slow reactions, gradually forming more complex compounds over thousands or millions of years in an environment almost completely frozen. Among the coldest known regions, the cosmic microwave background sets a baseline, bathing the universe at roughly 2.7 Kelvin, yet ultra-cold nebulae and molecular clouds can reach temperatures even lower than this local radiation floor, demonstrating that local dynamics can overcome universal thermal limits under certain conditions. Observations with far-infrared and millimeter telescopes have mapped these regions in exquisite detail, revealing filamentary structures, clumps, and variations in molecular density that highlight the complexity of chemical and physical processes at play even at the coldest extremes. In regions of star formation, ultra-cold cores within molecular clouds act as incubators for future stars, where the low temperature slows thermal motion, allowing gravity to dominate and initiate collapse while preserving molecular and dust structures critical for chemistry during the earlier stages of stellar evolution. The interplay between turbulence, magnetic fields, and temperature in these clouds produces a heterogeneous landscape, where dense cores, low-density envelopes, and filamentary bridges coexist, each maintaining slightly different chemical compositions and temperatures, forming a mosaic of ultra-cold conditions. Spectroscopy of molecules such as ammonia, formaldehyde, and carbon monoxide reveals subtle temperature differences, kinematic flows, and chemical gradients, showing that even in seemingly uniform ultra-cold clouds, the internal environment is dynamic with pockets of slightly warmer gas influencing reaction pathways. Dust grains covered in icy mantles are particularly important in these regions, providing surfaces for slow chemical reactions, allowing the formation of complex organics and protecting molecules from destructive ultraviolet and cosmic radiation, creating long-lived chemical reservoirs that may eventually seed new planetary systems. Ultra-cold regions also illustrate the limits of physical interactions, as low kinetic energies suppress collisional dissociation of molecules, stabilize fragile chemical bonds, and maintain coherence within gas and dust structures over astronomical distances, demonstrating that the coldest parts of space are also highly ordered in certain respects. Comparisons between the Boomerang Nebula, preplanetary nebulae, and diffuse molecular clouds reveal a continuum of ultra-cold conditions, with each environment exhibiting unique combinations of expansion, shielding, density, and chemistry, highlighting the variety of processes capable of producing extreme cold in nature. These ultra-cold environments are not entirely static. Small-scale turbulence, filamentary flows, and radiative interactions continually redistribute energy, ensuring that while temperatures remain near absolute zero, dynamics continue to influence chemical and structural evolution on both small and large scales. One of the more surprising insights from recent observations is that the coldest pockets are often chemically richer than slightly warmer surrounding regions, because low temperatures preserve molecules that would otherwise be destroyed, suggesting that ultra-cold conditions are not a hindrance to chemistry but a facilitator of complexity. The combination of slow chemistry, dust shielding, and radiative processes creates environments where even fragile organics can accumulate over extended periods, forming potential building blocks for prebiotic chemistry well before the formation of planets or dense stellar cores. Observations of these regions also reveal hierarchical structures, where filaments intersect to form dense nodes. Low-density envelopes surround these cores, and ultra-cold temperatures are maintained throughout, indicating that physical architecture and chemical processes are intimately linked in regulating the coldest regions. Interestingly, ultra-cold environments are found not only in star-forming regions but also in isolated globules, planetary nebula remnants, and the outskirts of molecular clouds, demonstrating that extreme cooling is a widespread phenomenon, shaped by local density, expansion, and shielding rather than universal temperature alone. The study of these ultra-cold regions informs our understanding of galaxy evolution, as the preservation and eventual mixing of cold, chemically rich gas into larger clouds can influence the composition of future generations of stars and planetary systems. Submillimeter and far-infrared imaging reveal that the finest structures, often spanning only a few hundred astronomical units, can maintain ultra-cold temperatures, allowing for detailed studies of chemical gradients, filamentary flows, and the role of dust grains in mediating both chemistry and energy transport. Beyond the Boomerang Nebula, regions such as the L183 and Barnard 68 molecular clouds exhibit temperatures barely above 3 Kelvin, revealing that ultra-cold conditions are not unique to dying star envelopes, but occur in relatively quiescent interstellar environments, where the slow accumulation of gas and dust allows dense cores to reach extremes of cold without being disrupted by stellar radiation. These clouds are primarily composed of molecular hydrogen, along with traces of carbon monoxide, ammonia, and other molecules that act as key traces for astronomers studying density, temperature, and chemical composition, demonstrating that even the coldest regions harbor measurable chemical richness. In Barnard 68, for instance, high-resolution observations show that the core is nearly isothermal, with minimal temperature variation across hundreds of astronomical units, allowing gas to remain stable while gravity gradually pulls material inward, forming a potential site for future star formation. The ultra-cold conditions in these clouds suppress thermal motion, so molecules collide less frequently, preventing high-energy reactions that could otherwise break chemical bonds, which helps preserve fragile species and maintain a chemical record spanning millions of years. Dust grains coated with icy mantles enhance this preservation by providing surfaces for slow chemical synthesis, allowing small molecules such as CO, H2O, and NH3 to gradually combine into more complex organics while being shielded from destructive radiation and cosmic rays. Spectroscopic studies reveal that despite extremely low temperatures, rotational and vibrational transitions of molecules still occur, emitting faint signatures that can be detected with millimeter and submillimeter telescopes, providing astronomers with maps of density, velocity, and chemical composition. Velocity measurements show subtle inflows within these ultra-cold cores, indicating that gravitational collapse is beginning, yet the extremely low temperatures slow the process, allowing detailed study of early-stage star formation and the influence of cold chemistry on molecular evolution. Filamentary networks connect multiple cores within a single cloud, creating a dynamic environment where ultra-cold gas flows along structured paths, turbulence is dampened, and chemical reactions proceed at rates determined by the balance of temperature, density, and shielding. The interplay between magnetic fields and low-density gas in these clouds provides further stabilization, preventing collapse in some regions while allowing cores to condense in others, showing that ultra-cold environments are structured and regulated by a combination of physical and chemical factors. Observations of molecules such as N2H+, NH3, and H2D+, illustrate that isotopic ratios and chemical abundances are preserved in these ultra-cold conditions, offering astronomers a window into the initial chemical composition of star-forming regions before thermal processes alter the molecular inventory. The chemical networks within these clouds suggest that even in extreme cold, reactions leading to complex organic molecules can occur, albeit slowly, raising the possibility that prebiotic chemistry begins long before planets or stars fully form, seeded by ultra-cold environments. Temperature gradients, though subtle, play a critical role, as slightly warmer pockets near embedded protostars can catalyze reactions that are otherwise suppressed in the coldest zones, creating localized chemical diversity that contrasts with the surrounding ultra-cold gas. Dust grains also influence thermal balance by absorbing and re-radiating energy, creating small-scale variations in temperature that drive chemical heterogeneity, with some icy mantles serving as long-lived repositories for complex molecules that may later disperse into the broader interstellar medium. Comparison between the Boomerang Nebula and these quiescent molecular clouds reveals that ultra-cold chemistry is not confined to dynamic stellar ejecta. Instead, slow, protected, low-density environments can achieve similarly extreme temperatures while maintaining molecular diversity and structural integrity. The detection of deuterated molecules such as DCO+ and N2D+ provides additional insight into cold chemistry, as these isotopologues form preferentially under ultra-cold conditions, acting as markers for the most extreme low-temperature environments within molecular clouds. Filaments and dense cores within these clouds show evidence of slow accretion flows, turbulence damping, and gravitational focusing, illustrating that ultra-cold gas behaves in highly organized ways that facilitate both chemical preservation and the eventual formation of stars and planetary systems. The combined effects of shielding, low temperatures, and dust-mediated chemistry mean that molecules can survive for millions of years, maintaining isotopic signatures and chemical fingerprints that inform models of galactic chemical evolution and the enrichment of future stellar nurseries. Even in regions where cosmic rays penetrate, the ultra-cold temperatures slow reaction rates, allowing molecules to persist despite potential ionization events, and demonstrating that extreme cold provides resilience against otherwise destructive forces in space. The diversity of ultra-cold environments, from dynamic preplanetary nebulae to quiescent molecular clouds, highlights the universality of low-temperature processes and the ability of the cosmos to sustain chemistry, structure, and energy balance under conditions that approach absolute zero. Observational campaigns combining millimeter wave spectroscopy, infrared imaging, and submillimeter mapping continue to reveal intricate filament networks, clumps, and ultra-cold cores, allowing astronomers to study chemical evolution in real time and connect the physics of extreme cold with the origins of molecular complexity. The persistence of ultra-cold gas in isolated globules and dense cloud cores emphasizes that extreme low temperatures are not merely a byproduct of stellar activity, but arise naturally from density, shielding, and expansion dynamics, creating environments where chemistry, structure, and physics interact over astronomical timescales. Ultra-cold nebulae like the Boomerang L183 and Barnard 68 illustrate that temperature alone does not define the chemical or structural complexity of a region, as even environments just a few degrees above absolute zero display filaments, clumps, and cores that organize gas and dust into coherent patterns observable across thousands of astronomical units. Within these filaments, dust grains play a central role, as their icy mantles provide surfaces for molecules to adhere, migrate, and react, enabling slow chemical synthesis that gradually produces more complex compounds over tens of thousands of years while preserving fragile species from radiative destruction. Deuterated molecules such as DCO+, N2D+, and ND3 are abundant in these ultra-cold environments, forming preferentially under low temperature conditions and acting as tracers for identifying the coldest, most chemically rich pockets within molecular clouds and preplanetary nebulae. Filamentary networks often converge to form dense nodes, where gravitational forces dominate and gas begins to accrete toward potential star-forming cores. Yet the ultra-cold conditions slow thermal motion, allowing these structures to remain stable while chemistry continues at a controlled, measured pace. Temperature gradients, though subtle, influence chemical diversity within these regions, as slightly warmer pockets near embedded protostars or external radiation sources can drive reactions that are suppressed in the coldest zones, producing localized complexity that contrasts with the surrounding ultra-cold gas. Observations using submillimeter arrays reveal that turbulence in these clouds is highly damped, allowing filaments to remain coherent and dust grains to maintain alignment, which stabilizes the ultra-cold structures and facilitates long-term chemical preservation across spatial scales, ranging from hundreds to thousands of astronomical units. Shielding by dust and gas ensures that molecules within ultra-cold filaments survive the impact of cosmic rays and residual stellar radiation, allowing fragile organics and isotopologues to persist for millions of years, effectively acting as chemical time capsules for future star-forming regions. Spectroscopic mapping has demonstrated that these ultra-cold clouds contain gradients in chemical composition, with dense cores enriched in deuterated species, while the surrounding low-density envelopes remain dominated by simpler molecules, illustrating how structure and chemistry are intimately connected under extreme cold. Dust grains coated in ice further regulate thermal balance, absorbing ambient radiation and re-emitting energy slowly, which prevents heating of the surrounding gas and maintains ultra-cold temperatures conducive to continued molecular preservation and chemical synthesis. Comparisons between ultra-cold molecular clouds and the Boomerang Nebula highlight the diversity of cooling mechanisms, showing that adiabatic expansion dominates in stellar ejecta, while radiative and collisional processes prevail in quiescent interstellar clouds, yet both environments achieve temperatures that challenge conventional expectations. Molecular diversity in these ultra-cold regions is remarkable, as observations reveal both simple diatomic molecules and more complex organics, suggesting that extreme cold does not hinder chemical evolution but instead provides a controlled setting where molecules can survive and react over extended periods. Isotopic ratios within ultra-cold cores provide additional insight into chemical pathways, as the enrichment of deuterium and other rare isotopes reflects fractionation processes that occur preferentially under extremely low temperatures, preserving a record of the conditions under which the molecules formed. Radiation shields created by dense filaments and dust clumps allow these ultra-cold cores to retain chemical signatures that would be destroyed in more exposed environments, indicating that the physical arrangement of matter is just as important as temperature in determining chemical outcomes. Filament intersections are particularly rich in chemical activity, as density enhancements promote localized reactions while ultra-cold temperatures stabilize products, resulting in nodes with higher molecular complexity compared to the surrounding low-density gas. Observational campaigns using millimeter wave and far infrared instruments have confirmed that ultra-cold regions are neither uniform nor static, but instead host subtle flows, microturbulence, and filamentary motion that collectively shape both the chemical landscape and the structural architecture of these clouds. The persistence of fragile molecules over millions of years suggests that ultra-cold regions may serve as cosmic reservoirs, storing prebiotic material that can later be incorporated into newly forming stars, planets, and ultimately the building blocks of life. Even in regions exposed to external radiation or shocks from nearby stellar activity, ultra-cold filaments often retain their integrity, demonstrating that low temperatures combined with dust shielding and magnetic alignment create a resilient environment for both chemistry and structure. The synthesis of complex organics within these ultra-cold zones occurs slowly but steadily, with icy grain surfaces catalyzing reactions that would not proceed efficiently in warmer conditions, illustrating that extreme cold can act as both a preservative and a facilitator of chemical evolution. Comparisons between different ultra-cold environments reveal patterns in chemical enrichment, temperature regulation, and structural coherence, suggesting that despite variations in density, turbulence, and radiation exposure, the fundamental processes governing ultra-cold regions are universal across the galaxy. Observational techniques that combine spectroscopy, high-resolution imaging, and velocity mapping continue to uncover new filaments, dense cores, and microenvironments, allowing scientists to connect physical processes with chemical evolution and to track the long-term development of molecules in these extreme environments. In this way, ultra-cold regions emerge as active participants in the cosmic cycle, preserving molecular diversity, regulating chemical reactions, and influencing the formation of future stars and planets, demonstrating that cold is not a barrier but a vital component of interstellar chemistry and structure. As ultra-cold regions extend across the galaxy, from isolated molecular clouds to the envelopes of dying stars, the patterns that emerge reveal a delicate balance between temperature, density, radiation, and chemistry, showing that even the coldest corners of space are highly structured and chemically active rather than empty or inert. The interdependence of dust, gas, and molecular species means that no single factor determines the chemistry. Instead, ultra-cold conditions arise from the cumulative effects of shielding by dust, slow thermal motions, and the subtle flow of energy through radiative and collisional processes. In the coldest filaments, microturbulence creates localized density variations, allowing pockets of gas to experience slightly different temperatures and chemical pathways, illustrating that even in environments near absolute zero, dynamics continue to shape the molecular landscape. Studies of isotopic ratios within ultra-cold cores indicate that fractionation processes proceed efficiently at low temperatures, producing enrichments in deuterium and other rare isotopes that serve as markers for the most extreme cold and provide clues to the history of molecular synthesis in these regions. The resilience of ultra-cold molecules demonstrates that low temperatures act as a stabilizing force, preserving fragile chemical species that would otherwise be destroyed in warmer environments, and creating reservoirs of material that may later contribute to star formation and planetary systems. Observational campaigns across multiple wavelengths, from far infrared to millimeter, reveal the intricate interplay between filaments, cores, and low-density envelopes, showing that ultra-cold regions are not homogeneous but instead composed of interwoven structures where chemistry and physics are inseparable. Dust grains act as both catalysts and protectors in these environments, with icy mantles enabling slow chemical reactions and providing shielding from ultraviolet radiation, cosmic rays, and thermal fluctuations, allowing complex molecules to accumulate over tens of thousands to millions of years. In filaments connected to multiple cores, gas flows are channeled along structured pathways, with turbulence dampened and chemical reactions proceeding at controlled rates, demonstrating that ultra-cold regions are dynamic yet stable, balancing motion with preservation. Molecular diversity within ultra-cold regions highlights that extreme cold does not limit complexity. Rather, it preserves intermediates that may form more intricate compounds once slightly warmer conditions allow further reactions, illustrating that cold is a facilitator of molecular evolution. Comparisons between quiescent molecular clouds and dynamic preplanetary nebulae show that different mechanisms, such as adiabatic expansion, radiative cooling, and low-density shielding, can independently produce ultra-cold conditions, yet the resulting chemistry and structure remain remarkably similar across environments. Deuterated molecules and isotopologs serve as traces of ultra-cold chemistry, allowing astronomers to map chemical richness, density variations, and temperature gradients, revealing that the coldest regions are also some of the most chemically informative and structured places in the universe. Observations of ultra-cold gas reveal that even minimal energy inputs, such as faint stellar radiation or cosmic ray interactions, influence chemical pathways subtly, creating localized variations that contribute to molecular diversity and highlight the delicate sensitivity of chemistry to environmental conditions. Dust alignment under magnetic field stabilizes filaments, allowing ultra-cold structures to persist over millions of years, while chemical reactions continue slowly on ice-coated grains, demonstrating that physical and chemical processes are intertwined even in extreme cold. Ultra-cold regions contribute actively to galaxy evolution, as their preserved molecules and dust grains are eventually mixed into larger clouds, seeding new star-forming regions and planetary systems with chemically rich material that originated in the universe's coldest corners. The gradual coalescence of ultra-cold cores into protostellar objects shows that low temperatures can coexist with motion and collapse, allowing the earlier stages of star formation to unfold in environments that maintain molecular integrity and chemical diversity. Even in regions subject to occasional shocks or turbulence, ultra-cold filaments remain coherent, highlighting that low temperatures combined with dust shielding, magnetic alignment, and low-density stabilization create resilient environments that preserve both structure and chemistry. The synthesis of organics on ice-coated dust grains continues at low temperatures, allowing molecules to accumulate slowly over long periods, providing potential precursors for prebiotic chemistry and demonstrating that extreme cold can be generative as well as preservative. Submillimeter and far-infrared imaging reveal that filaments, clumps, and cores retain ultra-cold temperatures while hosting complex chemical reactions, allowing astronomers to track both physical and chemical evolution and connect low-temperature physics with molecular complexity. The cumulative study of ultra-cold regions confirms that the universe's coldest places are not barren voids but highly active laboratories of chemistry, physics, and structure, where molecules survive, reactions proceed, and dust and gas organize in ways that shape the formation of future stars and planetary systems. In this context, the coldest regions serve as a bridge between dying stellar material, molecular clouds, and nascent stars, illustrating that extreme low temperatures facilitate continuity in chemical and structural evolution across cosmic timescales, linking the universe's past, present, and future.